Combustion scientists used direct numerical simulations to study the interaction between turbulence and chemistry in turbulent jet flames. Of particular interest are intermittent effects such as extinction and autoignition, which are difficult to identify in large-scale simulations. In this study, the data comprises over 350 million grid points and 230 time steps. The scalar dissipation rate, chi, is a derived quantity indicating the rate of turbulent mixing, thought to play an important role in autoignition and extinction events. Contours at locally varying ISO values in the chi field are thin, pancake-like structures that undergo compressive strain by turbulence. Scientists aim to characterize these structures according to their first three length scales: length, width, and thickness. The thickness is particularly relevant as it provides a direct measure of the local mixing scale. The primary focus in this project is to understand the relationship between the thickness and the mean temperature within these structures. Length scales are computed using spectral techniques. We parameterize each structure according to its first non-trivial eigenvector, and compute the length as a geodesic distance between the minimal and maximal function value. Subsequently, we extract contour curves as several ISO values. Fill these with a harmonic surface, and repeat the process to compute structure width. Finally, the thickness is computed as the length of contours in the harmonic surface. We have designed and built a general framework that supports feature-based statistical analysis and deployed it to study the scalar dissipation structures. First, we compute a merge tree of the scalar dissipation rate, providing scientists with a multi-resolution family of features that can be explored using a relative persistence measure. Statistics of interest are accumulated on a per-feature basis and are updated on the fly as the feature hierarchy is explored. Our tool supports aggregation of first through fourth order moments, min and max function values, in addition to length scale measurements. Using our plotting tool, cumulative distribution functions, histograms, time series, and relative persistence studies can be computed while varying the relevance to explore a wide range of statistics. This exploration is equivalent to reprocessing the entire input data with varying feature parameters, yet is performed on a commodity desktop computer. Our plot viewer and feature browser are linked. Selecting subplots will cause only those features whose statistics contribute to the subplot to be displayed. Scientists can also select a particular feature and obtain its associated statistics. In this study, we plot a series of CDFs of the average feature thickness conditioned on mean temperature. Features can have temperatures that span a large range of values. Hence, we first filter out features whose temperature variance is above a particular threshold. Aggregation of length scales, temperature mean, and variance for each feature allows for efficient updating of plots as scientists explore the threshold and temperature range settings. Our framework is a powerful tool for supporting feature-based statistical exploration. While we have successfully deployed it to analyze statistical properties of turbulent combustion structures, it can be applied to a broad set of scientific domains.